Hi everyone, this is the presentation of automatic detection of errors in LLM Large Benchmarks using frontier model consensus. My name is Cecilia Delgado Solórzano. I'm graduate research assistant at the School of Computing at Clemson University. I'm working at Human AI Empowerment Lab under the tutoring of Dr. Carlos Tosli. The content of this presentation is as follows: introduction, related work, methodology, results and discussions, and conclusion. Let's starting with introduction. Large language models have shown impressive capabilities in language tasks, but their reliability remains a concern, especially in real-world applications. Massive Multitask Language Understanding (MMLU) benchmark is used to evaluate LLMs across various subjects, but it might contain errors that affect accurate assessment. The study proposed a novel approach to detect potential errors in LLM benchmark by leveraging the consensus of multi-frontier models. The research focused on the MMLU benchmark and used prediction of from 15 state-of-the-art large language model to identify a subset of questions that we named hard that none of the models answered correctly. Surprisingly, manual analysis revealed that most questions in the MLLU hard subset were likely due to errors in the dataset itself rather than the limitation of the large language model. The approach offers advantages such as harnesses collective knowledge of multiple large language models efficiently narrowed down problematic questions and being scalable to other benchmarks. The finding has significant implications from the large language model development and deployment, emphasizing the need for more accurate benchmark dataset and evaluation frameworks. This method could contribute to advancing automatic error detection in large-scale datasets, potentially leading to cleaner and more reliable evaluation data for AI systems. The study highlights the importance of critically examining benchmark datasets used to evaluate AI models, as error in this dataset can lead to misinterpretation of model capabilities. Related work. The MMLU benchmark has been popular for assessing LLM performance across various subjects. Recent studies have questioned the reliability and accuracy of benchmark datasets, highlighting errors and biases. Research by Northcutt et al. Found that label error in test sets can significantly impact performance estimates and overestimate model capabilities. Chung and al. Proposed an automated method for detecting and correcting noise levels in large-scale datasets. Studies by Bender et al. And Weidinger et al. Focused on the limitation, biases, and ethical challenge associated with LLMs. The current work builds on previous research using frontier model consensus to identify potential errors in benchmark datasets. This approach aims to complement existing methods and contribute to more robust evaluation frameworks from large language models. Methodology. We have the data collections. The study used prediction from three state-of-the-art large language models like ChatGPT Turbo, Anthropic, Cloud 3 Opus, and Gemini Pro. But we used 15 large language models as well. These models were chosen for their strong performance in natural language, understanding tasks, and their representation of current LLM capabilities. The benchmark MNLU consists of 50,908 questions, multiple choice, and covers 57 topics. In this diagram, we can see that the MLU hard focus on collective failures point of the frontier models. It was taken for Helm prediction collections, this enterprise. So from here, we identify that certain subset of questions that it has 332 questions, no model can correctly answer it. So to improve this benchmark quality, we try to see if the models has a consensus about the answer. That means we will try to see if 3 LLM has consensus or 5 LLM has consensus, or between all the 15 LLM that we are using has consensus, to see how we can find the errors in an automatic manner. An open coding exercise was conducted by 3 researchers to analyze the MMLU hard subset. Open coding involves assessing labels or categories to dataset or characteristics or terms. Researchers independently review questions focusing on required cognitive capabilities and domain knowledge. Surprisingly, a significant proportion of questions appeared problematic due to the dataset error and not to the LLM limitations. Errors included incorrect answer options, ambiguous phrasings, and inconsistencies with established knowledge. A manual exploration was conducted on the representative samples of MMLU hard questions. The exploration involved internet search to verify information related to the questions and answer options. Manual exploration confirmed clear errors in the dataset, supporting the open coding findings. And the findings suggest the MLLU hard questions are more likely problematic due to the dataset errors rather than the LLM limitations. We use the following metrics: accuracy, recall, F1 score, and precision. This was to compare the consensus between the 3 LLMs, 5 LLMs, and the dataset was as follows. The group of 3 LLM was with ChatGPT 4 Turbo, Cloud 3 Opus, and Gemini Pro. The 5 LLM is ChatGPT Turbo, Anthropic, Cloud 3 Opus, and Gemini Pro, Llama 370B, and Mistral 8 by 22B. The 15 LLM, we invite you to read the article to know all the list of this LLM that was included. And we named 2 different consensus. The minimum consensus is when the half of the group plus one has the same result, and maximum consensus means that all the LLM in the group has the same answer to the question. Results and discussion. Coding results. The open coding revealed a significant proportion of MLLUR questions were problematic due to the dataset errors. Each research chose 3 topics to validate the dataset answers. Coding cases were divided into 2 main sections. A problem is in the question that could be poorly formulated, missing information, incomplete, or controversial topics. Or the problem is in the answer. Correct answer not in the options. Marked answer incorrect. Special characters in options or ambiguous wording. About the metrics. A filtering process was conducted based on the LLM consensus mechanism. A minimum consensus is the agreement between half of the group plus one. The maximum consensus is the agreement among all LLMs in the group. Dataset question varied between 117 to 303 based on consensus mechanisms and number of LLMs used. Accuracy, precision, recall, and F1 score were calculated for a minimum consensus with 3, 5, and 50 LLMs separately, and maximum consensus with 3, 5, and 50 LLM was calculated separately. The efficacy of different consensus strategies for large language models is demonstrated in Table 1. We can see that the consensus minimum and maximum, in general, the consensus maximum has a better performance in accuracy, recalls, and an F1 score. Nevertheless, we need to see how is the question, the number of questions that it was detected. And if we compare this, the minimum consensus in the 3 groups, it was detecting more questions. In this case, overall, we can see that the 5 consensus of large language model with the minimum consensus has a performance that could be acceptable in terms of the number of LLMs used and the number of questions that was detected with this method. The implications for this large language model evaluation and deployment. The study findings have significant implications for evaluating and deploying the large language models in real-world applications. Identifying errors in benchmark dataset ensures more accurate assessment of large language model performance. The approach of using frontier model consensus to identify problematic questions can be applied to other benchmarks. This method can lead cleaner, more accurate datasets for fair and reliable evaluations of AI systems. Identifying and mitigating benchmark errors guides the development of more reliable and trustworthy large language model. Improved benchmark accuracy is crucial in domains where large language model outputs inform decision-making or provide assistance. Future work. The Future research suggestions include extending the approach to other benchmark datasets across different domains and tasks, developing automated tools for detecting and mitigating errors in datasets. Proposed automated tools could use machine learning techniques like anomaly detection or clustering algorithms, and development of such tools could enhance efficacy and scalability of error detection in large-scale datasets. Conclusion. The approach can improve big data analytics across multiple sectors, leading to more informed decision-making and reduced risk. The study serves as a stepping stone towards developing more robust error-resistant dataset and analytical tools. It emphasized the importance of continuous validation and improvement of data resources in the area of AI and big data analytics. Thank you so much.